Welcome to The White Space, a podcast where we talk about data centers in a simple and practical way.
Welcome to the deep dive. Today, we're digging into something absolutely essential, but, mostly invisible. The real backbone of our digital world. Everything you do online, that video call, streaming a movie, grabbing info from the cloud, it all relies on this huge, complex, and constantly changing infrastructure. We're going to look at how data actually travels, where it's stored, and maybe the most surprising part, how it's kept cool. Seriously cool. This is really about understanding a massive shift in how our online life is powered, and we'll get into the companies and the tech making it happen.
You've nailed it. The amount of data we're creating and using isn't just growing, it's exploding. It's just phenomenal. And that explosion means we need more and more of the physical stuff, the infrastructure to handle it all. Understanding how this has evolved isn't just tech talk. It's fundamental to grasping our connected world and, frankly, where it's headed.
Okay, so let's unpack this. When we say digital infrastructure, what are we actually talking about? What are the core bits that make everything online just work?
Right. So at its heart, this whole digital infrastructure ecosystem kind of rests on a few key pillars. First up, you've got the data centers. Think of these as like huge specialized warehouses. They store, process, and dish out information. The internet's brain, basically. And they come in different flavors. On-premise for one company, colocation where lots of companies share space, or those massive cloud data centers run by Google, Amazon, Microsoft.
Got it. So data centers are the nerve centers. But how does information get between my phone, say, and one of those centers, maybe halfway across the world?
Good question. That's where fiber and spectrum are crucial. That's the physical network. We're talking about these incredibly thin glass strands, thinner than your hair, carrying data as pulses of light super fast over huge distances. Think of them as the data superhighways. Spectrum, on the other hand, is invisible. It's the radio frequencies floating through the air. That's what lets our mobile devices talk wirelessly, connecting us to those fiber highways. So yeah, highways and airways for data.
Okay, highways and airways. Makes sense. But what connects my specific device, my smartphone, to that big network?
That's the job of towers. Those vertical structures you see everywhere, they're the bridge connecting mobile devices to the internet. And it's not just the big macro towers. It also includes smaller stuff like small cells you might see on lampposts or distributed antenna systems inside buildings. They all work together. And then there's one more layer, kind of enabling everything else, tech-enabled infrastructure and the services. This is basically about making all that traditional infrastructure, the data centers, the fiber, the towers, smarter and more efficient using technology. Plus, it covers all the maintenance needed to keep it all running, 24/7.
Wow. Okay, when you break it down like that, you really get a sense of the scale. And here's where it gets really interesting. I saw this projection. Worldwide data creation. Expected to grow at roughly 29% compounded annually through 2035. So we went from about 47 zettabytes in 2020 to a predicted, 2,142 zettabytes in 2035. A zettabyte is a billion terabytes. So that's like going from 47 billion desktop hard drives worth of data to over 2 trillion. It's just hard to even picture.
Exactly. And that number, that mind-boggling growth, it directly fuels this relentless demand for more computing power, which in turn means we need more digital infrastructure, more data centers, more fiber, more everything.
Yeah.
And a huge driver, maybe the biggest driver right now for spending across this whole ecosystem, it's AI. Artificial intelligence.
Yeah.
AI needs incredible amounts of processing, which means tons of power, and generates a lot of heat that needs managing, especially inside those data centers.
Right, the heat. Okay, let's zoom in on data centers then. How do we get from like old school computer rooms to these super dense high-tech facilities we have today, especially the cooling part?
Oh, it's quite a story. Back in the 80s, with the big mainframes, we call them computer rooms or DP rooms, data processing. And they were kept really precisely controlled, usually around 72 degrees Fahrenheit, 50% humidity. Very specific. And here's something interesting. Those early mainframes, like some IBM models, they often use water cooling, had chillers right there in the room. The humidity control wasn't just for the machines either. It was critical to stop static electricity messing with the dot matrix printers, causing paper jams. I remember getting shocks all the time.
Wait, water cooling was there from the start. That is surprising. I always assumed it was this brand new thing driven by AI. So what happened? Why did air cooling dominate for so long?
Yeah, it's funny how things come full circle, isn't it? The big shift happened maybe early 90s, definitely by 2000, when we got those smaller rack-mounted one-use servers, the pizza boxes. Suddenly you could pack a lot more compute power into a single cabinet, a rack. People started talking about 20 kilowatts per rack, which was huge then. For perspective, even today, the average is still maybe around 8 kilowatts. But the industry figured out how to cool those higher densities, even up to 50 kilowatts a rack, pretty effectively with just air. And back then, air felt, well, safer, less risk of leaks, And it was generally more cost-effective than plumbing water everywhere, so air became the standard.
Okay, but you mentioned modern data centers can run hotter now, and something called delta T. How does that work for efficiency?
Right. So today, we intentionally run data centers at higher temperatures, and we manage the delta T very carefully. It's all about saving energy, being more sustainable. It's possible because the IT gear itself can handle it now. Standards from groups like HAE, they set HVAC standards globally, and NEBS for network gear, they've shown higher temps don't hurt reliability like we used to think.
So what is delta T exactly?
It's a simple concept, really. It's just the difference in temperature between the cold air going into the servers and the hot air coming out after it's picked up heat. So if you supply air at, say, 75 degrees Fahrenheit, and it comes back at 95 degrees after cooling the equipment, your delta T is 20 degrees. A higher delta T means your cooling system is working more efficiently. Each bit of air is grabbing more heat. We achieve that with really precise controls, especially variable speed fans that adjust airflow constantly.
Okay, makes sense. So higher temps, smarter air cooling.
Mm-hmm.
But now, with AI really pushing power density, it sounds like we're back to looking seriously at liquid cooling again.
We absolutely are. The buzzword now is liquidification. It means upgrading older data centers, ripping out those refrigerant-based systems, the DX units, like big ACs, and putting in chilled water or other liquid cooling systems that can handle AI loads. Because frankly, the heat generated by some AI chips is just so intense, traditional air cooling is hitting its limits. It might actually become obsolete for those really high-density racks.
So what are the big pluses of this liquidification, and what are maybe the downsides or difficulties?
The upside is huge, primarily energy savings. Liquid cooling can potentially slash the power used by the cooling system by 50% or even more. That could take a data center's PUE power usage effectiveness, a measure of efficiency from maybe 1.8 down to 1.3 or lower. That translates to millions in saved energy costs. Big sustainability win too. But yeah, it's complex. Retrofitting means dealing with the weight of liquids, potentially reinforcing floors. You've got to install all new piping, and you have to do it very carefully in phases because the data center usually needs to stay live during the upgrade. It's tricky.
And it must be hard to plan, right? With AI evolving so fast, how do companies know exactly what kind of cooling they'll need or how much liquid versus air?
That's the million-dollar question, really. And it's led to some clever solutions. There's this hybrid unit called Cool Phase Flex, for example. It came out of a collaboration between Vertiv and Compass data centers. What's neat is it can handle either an air-cooled load or a liquid-cooled load in the same unit. That flexibility is key because, like you said, nobody's totally sure what the mix will be on day 1 or day 100 for these AI setups. And they developed it incredibly fast, about 9 months from the initial idea to shipping the first units. That's light speed for this industry. It even has built-in battery backup, a UPS, just for the liquid cooling pumps because you cannot have that flow stop.
Wow, 9 months is impressive. That kind of rapid response is critical. Okay, so speaking of Vertiv, let's switch gears a bit and talk about the companies behind this tech. Who are the players and how did they get here?
Sure. Well, a lot of this history ties back to a company called Liebert, founded way back in 1965 by Ralph Liebert. They basically invented the precision computer room air conditioner, the CRAC unit, really pioneered keeping those early computer rooms stable. And later, around 77, they got heavily into UPS systems too, uninterruptible power supplies, battery backups to keep things running during power outages. They became the standard.
Right, Liebert. I've seen that name. How did they end up part of a bigger company?
Yeah, so Liebert Corporation was bought by Emerson Electric back in 1987. Then fast forward to 2000, Emerson bundled Liebert together with some other critical infrastructure businesses they owned, like ASCO, which makes transfer switches, and they formed Emerson Network Power, or ENP. So for about 30 years, Liebert products were essentially under the Emerson umbrella, a big part of their offering for data centers and telcos.
Okay, so Emerson Network Power, and then Vertiv emerged from that. How did that split happen?
Exactly. In 2016, Emerson decided to sell off ENP. They sold it to a private equity firm called Platinum Equity. The thinking inside Emerson, apparently, was that Emerson's strength was as a best cost producer, making lots of variations of things like compressors or, garbage disposals with product designs that might last 20 years. Network Power, though, needed much faster innovation cycles, new product platforms every 3 years sometimes. It just didn't quite mesh with Emerson's core model. So ENP was spun out, rebranded as Vertiv in 2017, and then Vertiv went public a couple of years later, around 2019 or 2020. But you still see the Liebert name on a lot of Vertiv gear today. It's a strong brand.
What's fascinating here is Vertiv's performance since becoming independent. The numbers are pretty staggering. Stock price up over 100% this year, market cap quadrupled. How did they pull off such a turnaround?
It really is a remarkable story. It boils down to a massive operational transformation. Their operating margin, for instance, went from about 8% in 2022 to nearly 19% projected for 2024. That's more than double. And cash flow swung wildly from negative $260 million in 2022 to positive $800 million in 2023, all while growing revenue by 20%. It's quite something.
They mentioned moving finance to the front end. That sounds interesting. What does that mean in practice? Can you give an example?
Yeah, it's a key part of their strategy. Instead of finance just, reporting the numbers after the fact, they embedded finance folks right into the operational processes. Take sales quoting, for example. For a big data center project, finance isn't just reviewing the final bid. They're involved up front, analyzing the profitability of different configurations, checking supply chain costs in real time, assessing risks before the quote goes out. They even had finance staff take the same product training as new salespeople worldwide, so everyone understands the tech and the market dynamics. It allows them to be faster, smarter, and more profitable. The CFO, David Fallon, often says his job is to be paranoid, always looking for what could go wrong or what opportunity they might miss. And this focus on innovation isn't entirely new. They connect it back to things like acquiring Coology, that liquid cooling company, back in the early 2000s. It seemed way ahead of its time then. But the tech they gained from that, like pumped refrigerant economizers, ended up being crucial for today's CoolPhase Flex hybrid cooler. It's foresight paying off, and they're still acquiring. They bought CoolTerra last year, another liquid cooling specialist, and some chiller technology this year, specifically to beef up their portfolio for AI's thermal challenges.
It really shows how past decisions and continuous innovation build on each other. Okay, so data centers and cooling are obviously huge, but let's quickly pan back out to the wider ecosystem. What's happening with, say, cell towers or fiber?
Right. It's definitely not just about data centers. Towers are still seeing huge investment. It's driven by getting more capacity out for 4G and 5G, plus more and more people using smartphones. This forces what they call densification, adding more cell sites, often smaller ones, closer to users. Plus, a lot of existing tower portfolios are aging and need upgrades. Consider this. Mobile data traffic per device is expected to grow over 20% compounded annually for the next 5 or 6 years. That's a massive load that needs more infrastructure.
And fiber. We keep hearing about fiber to the home. Is that rollout really happening everywhere?
Fiber is seeing massive build-out, yes, but the picture is mixed. In the U.S., for example, we're still seen as underpenetrated. Fiber only made up about 21% of fixed broadband connections in 2023. Compare that to somewhere like Spain, which is over 84%. So huge opportunity there, especially connecting homes fiber to the home, or FTT. But the challenge is you get potential overbuild in big cities where multiple companies lay fiber down the same street, while smaller towns or rural areas, tier 2 or 3 markets, are still waiting for decent broadband. It's an access gap issue.
And the last piece, spectrum. That's the invisible part, the airwaves, right? What's the dynamic there?
Exactly. Spectrum is absolutely essential for anything wireless, and it's a finite resource. Governments control and allocate it. The opportunity is complying 5G using different bands, low band for coverage, mid band for a mix, high band for super speed but shorter range. The challenge, it's incredibly competitive and expensive to acquire licenses for the most useful low and mid band frequencies, usually through government auctions. It's a constant strategic battle for telcos to get the spectrum they need for current and future networks, like whatever comes after 5G, maybe 6G. How that spectrum gets used really shapes our wireless experience.
It's just amazing, really, tracing this evolution, this invisible foundation of our digital world. It's gone from those early specific computer rooms to this incredibly complex global web of data centers, fiber, towers, all interconnected. It really underscores the constant need for innovation, for smart adaptation, and you have to appreciate the people actually building and running this stuff day in, day out.
The unsung heroes, absolutely. And here's maybe a final thought to leave you with. As AI continues to just explode, demanding ever more processing power, think about how that pressure doesn't just push technology forward. It fundamentally reshapes the physical world. The buildings, the power grid, the cooling systems needed to support it. Our digital lives become intensely physical in new ways. What other unexpected challenges or maybe opportunities will pop up as this accelerates?
Welcome to The White Turns,
shape
a
the next
podcast
wave
where we
of digital
talk about
experience
data centers in a
and
simple and
something to
practical
ponder.
way.